I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day I die. No one really knows why gravity exists.
Okay, so as was just mentioned, I am interested in the fundamental nature of stuff. I started out working at CERN on the anti-proton decelerator, which is the only decelerator in the world. And over there, we can actually make antiprotons that are slow enough to combine with positrons to make atomic antihydrogen. This was like a really awesome experience as a young scientist. I got to go over there and build these big vacuum chambers, deal with like huge power supplies, golden electrodes like you see in that picture, really probing fundamental ideas about the nature of stuff. However, when I got to grad school, I totally switched my focus, and now I work on experiments that, instead of taking up a whole accelerator hall, fit on a single optical table. These are just some pictures from my lab. I basically study little tiny flakes of rocks that people grow in their labs, but these little tiny flakes of rocks have very interesting quantum mechanical properties. So why did I become so interested in studying these little flakes of rocks over a big accelerator type experiment? And I'm hopefully going to convince you today that these little tiny flakes of rocks have very interesting and in fact fundamental properties to be explored. So this field that I'm in now is called condensed matter physics, and probably not many people have heard of it before, despite it being the largest field of physics. So I'm going to try and paint a broad strokes picture of where our field fits into present-day physics research. So if we start from the basic building blocks of the universe, one thing that you hear a lot about in public science type talks is high energy physics research, where people are looking at very, very small length scales to determine the most fundamental building blocks of the universe. These are like the basic particles in the Standard Model. This is kind of like the periodic table of particle physics. If you build up from that, you get the particles that we're more familiar with, like protons and neutrons. Those go into atoms, and then there's a finite number of atoms that can exist in the world, and that is explained, or I guess documented, by the periodic table of the elements. Increasing the complexity now, we can take these elements in the periodic table and make compounds, and that's condensed matter. So, aka rocks. That's why I keep saying tiny flakes of rocks. And then once you increase the complexity even more, you get stuff that I can't really explain, like biology, salamanders, human emotions. All these things are too complicated for me. So we'll stick to the rocks. So condensed matter physics is a very broad field. It encompasses like a huge range of labs and researchers. There's people who grow the crystals. There's people who study the crystals, that's me. There's people who come up with the many-body quantum mechanical theories to explain these materials, that's the theorists. And then we're even branching out to include more applied type research towards quantum computation. Atomic physicists are getting on board, and then there's even more deep theory theorists who are finding connections between how we explain black holes with how we explain many-body quantum mechanical systems. Which is pretty interesting, but I won't talk much about that today. So as I mentioned, condensed matter is the largest field in physics, and this is the field where most people who are actually considered physicists work in. Our annual meeting is called the March meeting. It's put on by the American Physical Society. That's our professional organization. It's once a year, changes the city every year, and just to give you a sense of the scale, 11,000 people went to this meeting last time in Boston. And then this is just a plot showing you how many PhDs are awarded in different fields of physics, and condensed matter outstrips all the rest of the subjects. So my sort of inspiration for doing these public science talks is like, condensed matter physics is the physics of rocks, it's the physics of things we see, why things reflect light. It's also the physics that most people actually do. And yet it's the least represented in what people talk about sort of in popular science media. So I'm hoping to add some interest into our field here. So just a brief historical note before we get into the physics. There's actually interesting stories about why condensed matter physics is sort of this huge overarching field in physics. And there's an article that you can read about it published last year in Physics Today by this guy who is a historian of science at Oxford. And I'll just briefly, you can read more about it in a book that this guy wrote too, and since we're in a library, I figured I would mention the book. It's called The Solid State Insurrection. But I'll just give you a brief summary as to why this field is so huge. So, like around World War I, World War II, the interwar period, there was a huge need for technological development, and the government sort of started to pour more money into industrial physics research. Around this same time, APS was founded, and their original goal was to sort of maintain physics as a fundamental subject because most of the funding was going into industrial type physics. At the same time, there were a lot of changes happening in how science was actually done. So a lot of times when people think about like their favorite scientists, they think of like Newton or Einstein or Lord Rayleigh or someone who was like kind of alone working on these very fundamental problems. But now science is really done by many, many people across the whole world. It's a hugely collaborative effort. And we've moved on from like understanding the basic laws of quantum mechanics and the basic laws of like electrodynamics to studying more complex systems. So now physics is sort of done by the many instead of the few. And as more people got into this field, there's more branching out from fundamental ideas into more applied things. And that includes condensed matter physics. So post-World War II, APS founded a division of itself called solid state physics to sort of unify the rift between academia and industry. And research just sort of took off from there. The government invested a lot in funding solid state research, and also private research institutions started to pop up. The big example would be Bell Labs, where my boss actually worked. In 1945, Bell Labs started really investing in fundamental solid-state research. 1953, the seminal textbook on the subject was published by Charlie Cattell, who's a professor at Berkeley. And just from there, it took off and became the largest division of APS. So it's true, all these, yeah.
Arielle, I want the audience to know that I dare to interrupt Arielle because she said she welcomes questions during her talk as well as afterwards. So I'm going to ask one here. You say condensed matter.
Yes.
Would that include liquids, or are so few things in the universe liquid that it's just not?
So condensed matter kind of does include liquids. This is kind of a ties into the historical development of the field. I'm calling it condensed matter right now because that's what we sort of colloquially called it. When it was first, this like field was first founded, it was called solid state because they really were just studying like electronic properties of rocks and stuff that could be used for computers, for wartime efforts, et cetera, et cetera. But as the field grew, we sort of realized that what we're really trying to solve is many-body quantum mechanics. And that includes stuff like liquids or magnetic gases and other interesting materials like biological stuff. And so when I say condensed matter, I basically mean a whole umbrella including all of those things as well.
So maybe someday it'll be called many-atom physics?
Yeah, or many-body physics, yeah. So I'm hopefully going to get into that in a minute. So the solid state, like specifically like coming out of Bell Labs, that kind of research has proven extremely useful. Does anyone know what this thing is?
Transistor?
Yeah. This is a transistor. So it's the basic logic unit of all modern computation. And that's based on a material called silicon, which is a semiconductor. So probably in everyone's phone, everyone's computer, basically all modern solid state electronics, we have silicon, but people actually don't really know usually what it looks like. So I brought with me a couple of chunks of silicon to be shared around the room if you guys want to take a look. So I have two semiconductors here. these big blocks, some of them are encased by glass, those are silicon. And I just love silicon. It's like a beautiful material. It's also the most plentiful non-oxygen element in the Earth's crust. And it's the semiconductor that gives us all modern technology. I also have some germanium, which is very close to silicon in the periodic table. So I'm just going to pass this around to everyone, and everyone can look at the beautiful rocks that I spend all day looking at. So yeah, there's silicon, and then if you zoom in super close on those crystals that I just handed out to you, you'll see that it has a lattice structure where the individual atoms of silicon are arranged in a periodic structure that has specific characteristics. So, oops, yeah, this was invented in, the silicon transistor was invented at Bell Labs in 1947. So in the 70s, there's this rebranding that happened that I was just talked about in response to that question. So there's kind of a seminal writing on this, which is a paper published by Phil Anderson, sort of the godfather or grandfather of modern condensed matter theory. He's still alive, actually, so that just shows you how young some of these ideas are. But he came up with this idea that more is different, and I'll talk more about that in a little bit. So, yeah, just going to mention this really quick. In modern times, there's been like a lot of interesting arguments about where we should be putting our research money and like what's more important kind of as a physics community. Like for high energy theorists, really what's most fundamental is going down to those tiny length scales. But for us as condensed matter physicists, we can see fundamental things at larger length scales, and they also have applied purposes. So, like for example, there's this argument that the world only needs one CERN, and the US sort of disinvested from high energy in the 90s when they nixed the superconducting super collider experiment. And there's a similar debate going on in China actually recently about whether or not they should build a collider. So something interesting to think about if you're sort of interested in the geopolitical aspects of science. So yeah, after this rebranding, we can include all of these things in this description of my field. Now, you might have noticed that my talk is named Quantum Materials, not Condensed Matter Physics. Quantum Materials is a smaller subset of this broad umbrella that I'm a part of. And this rebranding, again, happened in like 2009, so more recently. And we said, well, we need a cooler like name for our field. How about quantum materials? And people were like, well, aren't all materials quantum? Isn't like quantum mechanics the foundation of everything? It's like, okay, yeah, you're right. That's a useful feedback. So we have to come up with a more specific definition, and this is what my boss says. Quantum materials are materials which host collective modes that defy a classical description. And these collective modes we call quasi-particles. So I'm going to speak a little bit more about that when I get into the science. Okay, so now I'm going to go into convincing you that we can study fundamental ideas in these material systems. Just for example, something that I like to show is a comparison between the properties of a very common metal, aluminum, and one that you maybe don't see so often, gold. Gold, and one that you maybe don't see so often, niobium. As you can see, both of these on the atomic level are just a nucleus with a certain number of electrons around them. But once you group them together and make them into their solid state form, the crystals in fact look very different. Gold has this shiny yellow color. Niobium has this silver metallic, or we would call it metallic color, with like very clear cleaving edges on the crystal where you can see the cubic crystal structure. And what looks even more different is the transport property of the materials. So gold is like your typical metal. As you bring down the temperature, resistance can go down. But niobium, as you bring down the temperature, once you hit 9 Kelvin, the resistance doesn't just go down, it drops to absolute zero. And that's a phenomenon known as superconductivity. So typically when you apply a voltage across a metal, the electrons get pulled across the potential difference, and that gives you a flow of current. but those electrons always scatter in the lattice, and so there's some heat generated, and that's from the resistance of the material. In these superconducting materials, the electrons can flow with zero resistance, and that happens in niobium. And there's no way you can predict that this amazing phenomenon would happen just by looking at a single atom of gold or at a single atom of niobium. Yeah.
Please remind us, a temperature of 9 Kelvin is kind of balmy, is that?
That's actually very cold. So room temperature is 295 Kelvin. Yeah, that's about 20 Celsius. It's kind of where we're sitting right now. Liquid helium is 4 Kelvin. Nitrogen is 17. Okay, so in order to understand why we see these amazing properties, we need to know a little bit about the quantum world. I'm not going to go into great detail about this, but I'm just going to give a brief primer. So when we get down to the scale where quantum mechanics actually matters, we're talking about very fast length scales, so like 10 to the minus 15 seconds, femtoseconds, and very small length scales, an angstrom, 10 to the minus 10 meters. It's about the size of an atom. So just going to talk about some basic building blocks here. First of all, our old friend, the electron. It's a particle that we all deal with all the time. And it has some properties which determine how it behaves. It has a mass, it has a charge, and it has a spin. And an electron is a fermion, which means it has a spin 1/2. So spin is kind of like an important property in piecing all these things together in quantum mechanics. And the basic idea of quantum mechanics that you may have heard before is that these particles are not just particles, they're also a wave of energy. So there's this equivalence between mass and energy. So particle, wave, and where the particle is actually located is described by a wave function. So it's not actually, it can't actually just be in one place at the time that before you measure it. Okay, so the second particle that we deal with all the time and that I deal with a lot working with lasers is the photon. So light is actually also a particle. It's massless. It has energy related to its frequency being its color, and a photon has a spin of 1, which means it's a boson. So fermions and bosons have fundamentally different statistics. Mainly, spin 1/2 fermions, you can't put 2 spin 1/2 fermions in the same energy state with the same sign of spin. Bosons, you can put infinitely many particles in the same energy state. And that sort of informs some of the properties that we observe in condensed matter. Okay, so now if we build up to a higher complexity scale, we put that electron in the atom. Now the electron is no longer just floating around in free space. It no longer just sees the isotropic world of the vacuum. It's confined by the potential of the nucleus. And this puts it into quantized atomic energy levels. This is sort of like the quantumness that we think about a lot. So the electron can only exist in certain energy states, which are defined by discrete steps. You can promote an electron. I'm representing electrons by those arrows for their spins. You can promote an electron to a higher energy state by sending in a photon. It absorbs that energy from the photon, and it goes up to a higher energy state, just like that. And this can be seen by the color of light, which is absorbed by the atom. So this little cartoon down here shows you like the spectrum of visible light, and then there's little dark lines at the bottom, absorption lines, where you might absorb a photon of a certain wavelength or energy corresponding to that jump in an energy level. So now we're going to increase the complexity even more and put that electron that's in that atom into a lattice. So instead of now being defined only by the confining potential of the nucleus, it's defined by the symmetry of the crystalline structure. And those energy levels that the electron was in before get sort of spread out into what we call a band structure. So this is what we look at a lot in condensed matter physics. Instead of just having energy levels, like discrete energy levels that the electron can be in, we actually have energy on the y-axis here, and then momentum on the x-axis. So there's many different states that the electron can be in depending on what its momentum is that are described by those lines you see on the chart.
Excuse me?
Yeah.
So in that diagram, some of those things look continuous, which surprises me because I thought quantum was more like binary, sort of.
Right, yeah, so these lines are continuous in the crystal momentum. So it's a little bit, so if you have this crystal lattice structure and you take the Fourier transform, you end up somewhere in momentum space, and that sort of gives you all these different locations kind of in the crystal where the electron can be.
If this helps.
Oh yeah, that might help.
There's that one right there.
Yeah, and there's still discrete energy levels. Like, so if the electron is here, this is what we call the gamma point. I'm sorry, I'm leaning onto jargon here. But the electron might be here, and then the quantum jump that you're expecting would be up to this point.
Is this at a momentum of that particle, or is this some property of the crystal?
It is at the, so these crystal momentum are defined by the crystal structure. So there's
So
momenta
that's
that
not
are
the
allowed.
momentum of a single particle. This is like some property of that lattice structure.
Yeah, so you have energy states which are like determined by the electrons that are on each of these atoms, but also by how those atoms are arranged. And how those atoms are arranged gives you this, we call it a dispersion relation in the crystal space. So instead of just like an atom having just a single, I guess, momentum associated with the transition, you have a dispersion of momenta defined by the symmetries of the crystal. Yeah, so in quantum mechanics, there's only like a couple problems that we can actually solve exactly, right? There's like the harmonic oscillator, there's the hydrogen atom, which is just a single proton and electron. There's like the x squared potential. There's only a couple problems that we can solve exactly. So getting these energy levels actually requires some approximation methods, and it becomes more complex. We have to sort of extract what we can from the symmetry properties of the crystal to understand how these electrons actually behave. And one of those, the most important symmetry in crystalline matter is translational symmetry, which I was just trying to describe, albeit perhaps poorly. But I use this picture from M.C. Escher to sort of describe it. So you notice there's certain centers here which look the same at different points in the image. And what you can do then is actually select those points. And then if you take the same image and translate it by a specific set of special directions, you retrieve the same image. So this is called translational symmetry, and these set of special directions we call the unit lattice vectors, and they define the unit cell of the crystal. And the properties that the crystal can have, like where that electron can be in that band structure, really depends on these symmetries. So I have with me something that I stole from the lab a couple hours ago. I'll put it back, I promise. But this is actually a gallium arsenide unit cell, or the yellow bars define the unit cell of gallium arsenide. This is a model of a gallium arsenide crystal. Gallium arsenide is another semiconductor. It's like silicon. Gallium is very close to silicon on the periodic table. It actually has the same crystal structure, but it has 2 times the atoms. So yeah, so a symmetry of this crystal would be like if you look at it from one orientation and then you like rotate it and that orientation looks different, then it breaks that symmetry. Or like if I'm looking at it here, and then I invert it, and it looks different, then that's breaking inversion symmetry. So depending on which symmetries the crystal can conserve or break, we get different properties. So I'll just let you guys look at this. It's kind of fun trying to like see which directions look the same. Yeah, silicon is the same structure.
Arielle, those are gallium atoms, arsenic atoms, and what are the little gold or yellow guys?
Yeah, so the yellow lines define the unit cell of the crystal.
No, but I mean, there are little spheres attached to the very bottom as if, those are just...
Oh, that's just for...
Okay.
So this model of gallium arsenide definitely breaks inversion because it has feet. So... yeah, okay, so this is what I mentioned before. More is different. So if you read Phil Anderson's article, which is actually very accessible, it was written in the 70s, and for someone who's interested in sort of the philosophy of science, I think this is a really good read. And his argument is that when the symmetries of the vacuum, just isotropic free space, are broken, and when the system size becomes large, and then we allow those system constituents to interact with each other. So I didn't mention this, but that band structure I showed is not only informed by the crystal symmetries, but also by the interactions between the electrons on each of the atomic sites. Solving the quantum mechanics problem for that quickly becomes intractable on large length scales, and fundamentally different properties can emerge. So finally, we get to the example of superconductivity. As I mentioned before, superconductivity is the flow of current with zero resistance. It was discovered by this Dutch guy in 1912. So he was the first guy to actually produce liquid helium, which is 4.2 Kelvin. And once he did this, he put mercury into it and measured just the resistance as a function of temperature, and then was extremely shocked to discover that the resistance dropped to actually absolute zero very sharply. So there's a few properties of superconductivity. One of them is this zero resistance thing, and another one is that they expel magnetic fields. So a common science demo that you'll see is this little magnet floating above a superconductor that's cooled down to below its TC. So when it goes superconducting, colloquially we call that TC, it's the critical temperature. So if this magnet has a magnetic field coming out of it, the superconductor won't let any of those magnetic field lines penetrate into the material, and it pushes the magnet up.
So there's no electricity involved in that at all. The bottom disk is just an ordinary
It's just a superconductor. Yeah,
Yeah,
it's probably like niobium or something. Yeah.
So the idea is that when that magnet floating above starts to fall out, or as you bring it down close to the superconductor, currents start to flow.
You can get eddy currents on the surface.
Oh, and that's what magnetically levitates the, wow.
So yeah, apart from all these cool things, superconductors have actually proven quite useful. One thing you can do with a superconductor is you can make it into a wire and then cool it down below its TC and put a current through it, and you can get a persistent current that will circulate basically forever until you go above the critical temperature. Sorry, my friends just walked in, so I'm distracted. So this has given us a lot of really cool technologies. One, for example, is MRI machines, which involve high magnetic fields. A couple other cool technologies are the South Pole Telescope, which is down at the bottom of the world studying cosmic radiation from the beginning of time. Pretty awesome. They use superconductors as their detectors. And then I keep mentioning CERN, but I'll mention it again. The magnets that the LHC uses are superconducting magnets. And then finally, more recently, people have been using superconductors to make qubits to try and build a quantum computer.
So I have a question. So it sounds like you're getting free energy, but you're not, when you say that wire, the electricity just keeps going.
Yeah.
But you're not, because you have to cool it down to a certain level or something? Is that the cost of it, or what's the...
Well, so you have to put a current in at first, I guess, but basically the electrons in that wire are moving around, but they're not dissipating any energy.
There's no resistance.
Yeah, so the
Because there's no resistance?
there's no resistance.
Okay.
Yeah.
Is it really zero, or is it just really
It's really
small?
zero.
Yeah.
Yeah.
So in a way, is this a kind of microscopic perpetual motion that was long said to be impossible?
I mean, it's not really perpetual motion. I don't think you're really like creating any new energy from it. You're just.
You're also doing no work.
Yeah.
So even though you're injecting energy, you're just storing that.
But you'd think just to measure the continuous, unimpeded motion of the electrons, to measure it would take some of their energy. And
Well, to measure it, you have to put in a resistor, and then it's no longer like a persistent superconducting loop.
but so it's not like trying to prove that the light's off in the refrigerator when you close the door, right? You open the door of the refrigerator, and the light goes on, but you're confident when you close it, the light's off, but you can't ever observe that. It just seems like you can't observe true superconductivity.
Yeah, you can see the. I mean, if you put if you're measuring transport, you have wires connected to your material, it's niobium, you cool it down, you're measuring the resistance, you will see it drop to zero. You won't measure anything. Yeah, and then also, I mean, if you have a coil, right, like the MRI, you can measure what the field is. The Meissner effect, which is the expulsion of magnetic field, which I mentioned before, has been measured. So there's a lot of measurable properties about superconductivity. Okay, so yeah, but to measure a current, you're going to need resistance. Anyway, okay, so this phenomenon, as I just mentioned, was discovered in 1912, but it actually was not explained until 1957. It got the Nobel Prize in '72. And the phenomenon needs quasi-particles. It needs these sort of emergent ideas to explain what's really going on. So this is what we call Bcs theory. This is what type 1 superconductors can be explained by. So remember I mentioned that electrons are spin 1/2, and you can't put two electrons in the same energy state? Well, it turns out if you're in a lattice and you have electrons flowing through a lattice of, imagine, positively charged atomic ions that are in the crystal, the opposites attract, right? So, oops, I went the wrong way, sorry. So the attractive potential from the electrons flowing through the lattice will sort of deform that lattice and pull the positive ions closer together. And this is sort of described as like a screening potential between the two electrons. So now those two electrons have a positive potential in between them, and they can actually pair up. You get a new particle, which is called a Cooper pair. You have two electrons in there, and now they have spin 1. So now they're a boson. They're not a fermion anymore. And they can all fall into the same energy state. So all of the electrons that are scattered into the lattice, we call this exchanging a photon in condensed matter, and they can all sort of condense into this superfluid condensate and transport electricity without scattering. So this is like what happens in niobium, which has that Tc of 9 Kelvin, but there's a whole zoo of these kind of materials where this phenomenon happens at higher temperatures. The most famous one is a class of materials called the cuprates, which people have been fighting about for 30 years. And these consist of copper-oxygen planks, and the superconductivity sort of emerges as a competition between insulating magnetic behavior and conducting metallic behavior. So this is a phase diagram that we would look at in trying to understand what's going on in these materials. And as you can see, superconductivity only occurs in a certain region of temperatures, and also concentration of carriers. So people can add like impurities to these materials, that's called doping, and that changes this value on the x-axis. And the superconductivity only occurs in a limited region of that phase diagram. So superconductivity has been an ongoing project since 1912 and since the discovery of the cuprates in like the 80s. Those are the cuprates again. And this is just a plot of superconducting Tc versus year. And people really want to try and understand what's going on in these high temperature superconductors. Because if we can make a room temperature superconductor, we can make power lines that can like transmit energy without any loss. It would be incredible, it would be amazing. Maybe we could have a quantum computer at room temperature. But the thing is that pairing mechanism between the electrons is not exchanging a phonon as we understand it in the type 1 or BCS type superconductors. It's something different and something that is still an active area of research. We're working on it. But the highest superconducting temperatures that have been recorded are actually in these hydrogen systems where people put them under extreme pressure. So if you look at this plot, the cuprates that I talked about, or sort of right here, you can see the discovery of cuprates in 1985, boosted Tc up to like 150. Hydrogen disulfide is up at like 200, but that's under like a huge amount of pressure, like comparable to like center of the earth type pressure. And then there was a paper on the archive last year with lanthanum tetrahydride at 294 Kelvin, room temperature superconductivity. I actually haven't followed up on this and seen if this is published. I don't know if anyone in the audience knows if this is published or not, but this is on this archive preprint server where physicists post all of their work before it's published. So if anyone is interested, you can jot down that number, and if you Google it, the paper will come up, and you can read about room temperature superconductivity under extreme pressure. So there's a continuing story in the saga of superconductivity. Who's heard of graphene? Yay! Okay, so graphene is this amazing material which is a single sheet of carbon atoms, and it has all these like incredible electrical and mechanical properties. People have been studying it for like many years, since like 2008 I think was when graphene was first exfoliated. And just last year it was realized that graphene can actually superconduct. Whoa! How do you make graphene superconduct? Well, you take two sheets of it, you put them on top of one another, and you start rotating them. And then once you rotate them to a magic angle, or 1.1 degrees, you change the fundamental unit cell of the bulk crystal. So remember I said with the unit cell you can describe the whole crystal? For graphene, it's just like one of these little hexagons. In twisted bilayer graphene, the unit cell becomes quite large and quite different. And you can make many different states with this compound. So this plot is a phase diagram for a twisted bilayer graphene, and the y-axis is temperature, so you can see it's very low temperatures, and then the x-axis is essentially the voltage that they apply to the twisted bilayer graphene. And these blue domes are where it superconducts, which is kind of incredible. But what's almost more incredible to me is on this same phase diagram you have metallic behavior and Mott insulating behavior. So just from this single material, changing the unit cell properties, we can see like basically the properties that we can find in any other material in the whole world.
Arielle, what is Mott?
Mott is a specific type of insulator. So an insulator is a material that does not conduct electricity very well. Sometimes that happens because the energy bands are separated, and sometimes that happens because of strong interactions between the electrons on the atomic sites. And that's what a Mott insulator is. So this is a totally new type of superconductivity. And in Los Angeles in 2018, where they announced this, people were like shocked and They say it's like a rock concert. I don't know if these people have ever been to a rock concert, but that's what it looked like. A few people in the room were actually there too. This is not a picture I took. I stole it from the internet, but I can attest to the fact that it was very crowded and very exciting at that time. This article is published in Nature, so if anyone wants to check it out, it's by Yuan Cao, who's a grad student at MIT.
I have a question for you. So why would somebody even think of twisting the graphene? Does that make any sense to you? How did they even think of doing that?
I think maybe there had some theoretical predictions. So, like, the way our field works is pretty cool because we can, like, make materials pretty quickly and, like, change experiments around a lot, and we also interact a lot with theorists. So I don't really know actually the whole story of how they got the idea to do this. I know they tried for like a long time, and it's actually pretty hard to get the angle exactly 1.1 degrees. They have to like take a layer of, you know, a whole like couple layers of carbon, exfoliate a single one, hold that at a specific angle, and then like rotate the bottom one and like carefully put it back down. And so it's non-trivial to make these. Apparently, there were some like weird papers from like a long time ago where people reported superconductivity in like graphite, which is like your pencil lead. I heard this from Pablo Arielle Herrera, who's the PI who did this work originally. He claimed that there's these early papers where people observe superconductivity in like pencil lead because of like weird stacking faults in the graphite in those layers. I haven't actually looked those up myself. I've been meaning to do that, but yeah. So yeah, as I said, we work very closely with theorists, and in light of this discovery, there's been like a huge like flourishing of work on this topic. And as of Friday, I went to the archive, which is the website I was just talking about, and just typed these words in, and there's 344 papers just including these words. So yeah, now we have, this is just apart from superconductivity and the whole graphene thing, there's a whole zoo of recently discovered new properties and phases in our field which we're interested in studying that have come up just in the last 15, 20 years. This is just a brief summary of some of them. I won't talk too much about them, but one that I've worked on, for example, is quantum spin liquids. So, since I have a little bit more time, I'm going to tell you a little bit about that. But first, here's where I work. This is the Lawrence Berkeley National Laboratory. If you are ever in downtown Berkeley and you look up on the hill, you can see this round pink building. That's actually a particle accelerator. Some people don't know that. It's an electron accelerator. They speed up electrons really fast and then slow them down or change their direction, and X-rays come out. So people use those X-rays to study stuff like the structure of crystals, and even for like biological type research, looking at proteins and stuff. So I don't work specifically there, although sometimes I do. My lab is right next door, and we do optics, so lasers, as I've mentioned many times. Oh yeah, okay, so these are the facts that I just mentioned a little bit about the ALS. Researchers from all around the world come up to this facility, and one fun fact that I like to tell people is that this building is actually a historic landmark. It was designed originally to house the 184-inch cyclotron that Lawrence had up on the hill, and that was like one of the very first particle accelerators like in the world. And the building was designed by Arthur Brown, who also designed Coit Tower. So it's just kind of fun. So what I specifically do in my little lab next to the ALS is I use optical techniques to study magnetism. So I'm just going to give you a brief...
Are cats involved?
No, I just always show this picture because that's how I feel like in the lab. So this is just a brief picture of the energy scales of light. Remember I said that a photon's energy is related to its color. There's many different types of photons depending on what color they are, and we can't see all of the colors that they can be. So down here in the low energy range we have like radio waves and electronic frequencies, and then as we increase the energy of the photon, we get microwaves. There's this little gap right here where there's the terahertz frequency range, which I work in sometimes. So we get over here, we get to the infrared, which is kind of like people use infrared cameras to see heat, for example. And then in the visible range over here, we have all the colors that we know and love. And then as you go up to higher and higher energies, you have ultraviolets, X-rays, etc. I don't really deal with those too much. And then these are some properties of materials that can be found in all of these different ranges. So at CERN, at the anti-hydrogen experiment, I was just measuring this one specific transition in hydrogen, which is right here. Now, in my lab, I can measure stuff all the way from the terahertz, which would be like magnetic resonances, phonons in the infrared, and then optical properties higher up into like the near infrared and the visible. So we use magnets every day, but what makes a magnet magnetic? Well, remember I talked about the electron having a spin. If you have an electron on each of the atoms, say our crystal is just a simple line of atoms, 1, 2, 3, 4, and then if you cool that guy down so that the electrons sort of stop moving around, the electrons in the orbitals on each of those atoms may align. And when they align, you have something called a ferromagnet. That's like the magnet that we typically think about when we think about magnets. An example being iron, like the magnet that you put on your refrigerator. To get them to line up all the same way, in like a macroscopic fashion, you usually have to cool it down in the presence of an external magnetic field. But there's another kind of magnetism, which is actually, I think, more interesting, and that's antiferromagnetism, where instead of now all the electrons wanting to line up in the same direction, they actually alternate. And antiferromagnets are pretty broadly interesting for reasons that I will mention later on. Now, when you're in this ordered phase of a magnet, you can excite the spins with, for example, a pulse of terahertz light, and they sort of move around in a collective mode, and that's called a spin wave or a magnon. And those are quasi-particle excitations of the magnetically ordered state, which we can see with optics. So yeah, antiferromagnetism is super cool because it gives rise to all of these like fundamentally like fascinating phenomena. As I mentioned, like superconductivity for the high TC stuff, all of this sort of emerges in a landscape where you have antiferromagnetic orders sort of competing with metallic states. Another thing that's like quite fascinating that antiferromagnetism may give rise to is the quantum spin liquid, which I'll talk about in a second. And then antiferromagnets can also give us sort of a new platform for computing or memory that we like to call antiferromagnetic spintronics, which is related to this third material, which I may not talk about, but I'm showing it anyways. So yeah, why do we get all these interesting properties from antiferromagnetism? Well, the classic example of this is if instead of having these guys just on a line, you have them on a triangle, okay? And then they want to interact antiferromagnetically. So for these two guys, it kind of makes sense. It's like, okay, this one wants to be up, this one wants to be down, but this guy at the top is sort of equally influenced by the two at the bottom. And so it doesn't really know where to point. And this is called frustration. Like, there's actually like a conference called like the Frustrated Conference, like, or the Frustrated Magnetism Conference. It's pretty funny. But now that I say it all the time, I don't think it's funny anymore. So the quantum spin liquid that I wanted to tell you about is a state that can emerge from the state of frustration. And the material that I studied specifically is related to a case called the Kitaev spin liquid, where instead of being on a triangle, you have your antiferromagnetic spins on these hexagons. And the Kitaev model was made up by this super weird guy called Alexei Kitaev, who was like a theoretical physicist just like working at home. And he came up with this idea that if you have a hexagonal arrangement of spins and then you have a different interaction along each of these 3 bonds, you end up with a highly frustrated state. So that even if you cooled this thing down to 0 temperature, the spins will never order. And that's the quantum spin liquid. And it just seems, first of all, super weird that you can like cool something down to 0 temperature and see no magnetic order. But the other weird thing is once you enter into this special state of matter, you can make excitations out of that state that look like very exotic fundamental particles that have not yet been detected in fundamental particle physics. The primary example that we have for the Gaia spin liquid is you can possibly make Majoranas. In particle physics, a Majorana is classified as a particle which is its own antiparticle. So for like a proton, you have a proton and an antiproton. For a Majorana particle, it is its own antiparticle. It doesn't have a partner. And this has so far not yet been discovered by particle physics, but perhaps it exists in this messy, disordered system. I think I see a question. Yeah.
What makes this a liquid? What do you mean by liquid?
Yeah, people always ask that question, and I think it's somewhat of a misnomer because it's actually still a solid, like the crystal doesn't like melt or anything, but it's just because the spins are not rigid. They're sort of freely moving around.
So it's true that glass is actually a liquid?
Glass is amorphous. So I would call glass a amorphous solid. But if you heat it up, it becomes liquid-like. Yeah. So yeah, this is what the material actually looks like. And this is what I love about this field. It's like we're talking about like Majorana quasi-particles out of a quantum spin liquid state that was like invented by some weird theory guy. And it maybe shows up in this rock. It's like, oh my God. I actually kind of don't think that it shows up in this rock, personally. There's some interesting, convincing evidence from a group in Japan, but there's still a lot of debate within the community, and people are sort of looking for this state, this highly disordered state. And it's a weird thing to look for because, like, there's not really like a fundamental signature, like, of this state which we can measure. We're sort of like kind of looking for the high level of disorder, which is a weird thing to look for. So yeah, let's see. So that's what the title image is, actually. This is just an illustration that someone made to illustrate the ruthenium chloride lattice being bombarded with neutrons. People use neutrons to study magnetic order as well as photons. So yeah, hopefully I've managed to convince you that condensed matter is a rich playground for new fundamental ideas in physics, and coincidentally, it also happens to be useful. Yeah, so that's basically the end of my talk. I have one cool video that I can show you, but I would like to ask for questions first. Sorry, I just realized this has a sticker that says Shreyas on it because he's my lab mate, and this was like his controller, and Shreyas is actually here. So it's just funny. Yeah. But does anyone have any questions about some of the stuff that I spoke about already, or?
A million questions.
Yeah.
Several slides back, quite a few back, you were explaining superconductivity by showing 2 rows of atoms, don't remember what atom it was, and the electrons between them.
Yeah.
Oh, yeah.
And then you showed 2 of those host atoms, the two there you go, yeah. I guess, let's say those positive ions marked in blue with the plus signs.
Yeah.
You said that 2 of them come together.
Yeah.
What motivates that? For instance, if any...
So, yeah, so this is not a super great illustration, and this is kind of like the more cartoonish explanation of what happens, but I think the picture might be bad, but basically what happens is the electron is like a negative charge flying through the lattice. The positive atoms on the outside are attracted to that negative charge, and move in. And so then as the electron moves by, there's a positive like region of charge sort of behind it from the deformed lattice. And then that can in turn attract another electron into this Cooper pair.
You mentioned the graphene before.
Yeah.
We think of the graphene as being, the two sheets of graphene as being the positive charges here, or is that just not a good?
It's not, that's not how it works. Yeah, we don't know how it works.
Oh, okay.
We're working on it. Well, I'm not.
But even
other
in
people are.
superconductivity and graphene doesn't happen between the two sheets? That's not, I'm sorry to say between the sheets without.
Yeah. I mean, obviously it has something to do with the fact that there are two sheets and that the size of the unit cell changes when you twist it. But it's still a work in progress understanding what causes superconductivity in that material. Yeah, we don't really know yet. It's just discovered last year. So.
What's a phonon?
A phonon is what we would call a quanta of vibration in the lattice. So this, like, what I'm describing as a deformation of the lattice, having like a positive charge, that could be understood as a phonon. So vibrational modes in a solid are also quantized, sort of like the energy levels of the electron in the atom. And we call those phonons, which are quasi-particles again. Since we just talked about superconductivity again, I can go through this whole thing and I can show you the video, which is super fun, that we made one Friday night in the lab as we were actually cooling down to study ruthenium chloride at low temperatures. So one phenomena that physicists were like super interested in for a long time was the superfluid transition in liquid helium. And it turns out helium, when it's cooled down at 4.2 Kelvin, if you have helium-4 atoms, if you pump on it, you can decrease the temperature more. And then at, I think 2.17, around 2 Kelvin, the helium-4 atoms actually pair up and no longer have spin 1/2 as they would individually, but have spin 1. And you get a superfluid condensate of liquid helium. And in our lab, because we're an optics lab, we have cryostats with windows. So we basically filled up this cryostat with liquid helium, pumped on it, and then you can watch that phase transition to the superfluid condensate, which is somewhat analogous to a superconducting condensate, happen. So I'll just play this really quick. There we are looking at the controller and seeing what the temperature is, and then we like awkwardly walk over and start filming the liquid helium inside that chamber. And we're pumping on it, so it's getting colder, bubbles are coming out.
Pumping on it means what?
So we have a vacuum pump attached to this system, and we're lowering the pressure in the chamber. So there's like a pool of liquid helium at the bottom, and then there's like some gas in there. It's usually maybe some leftover air or some helium that's being bubbled off, and we're pumping that out with a vacuum pump. So the pressure on the little pool of liquid helium is going down.
And when in a sense that liquid helium is boiling and it's turning from liquid to gas above?
As we're pulling it into the cryostat, it's boiling because it's touching like the hot edges of the cryostat. But pressure is related to temperature through the ideal gas law. So we can lower the pressure, we can also lower the temperature of the fluid. And so that's what we're doing here to drive the phase transition. So it's kind of like all going crazy because there's like, vibrations from the pump, it's boiling off on the edges of the cryostat, it's getting colder and colder, but at a certain point we hit the phase transition and it becomes completely transparent. And that's because now all the helium-4 atoms are paired up and they're all in their lowest energy state and they stop scattering.
At 1.959 Kelvin?
Yeah, that calibration might be a little off, but we're below 2. I think the transition is actually around 2. So that's just one fun thing that we This is like literally like Friday night and we were like doing this.
I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day I die.